Shashikant from Electrical Engineering Department, University Lucknow. Today I am going to discuss about the generation of pseudo-random numbers and pitfalls. Pseudo because generating numbers using a known method removes the potential of true randomness. Goal to produce a square arithmetic sequence number 3801 that simulates or imitates the ideal properties of random numbers Rn means random numbers. Important consideration for Rn routine first is the fast, next is the portable to different computers. Next, have sufficiently long cycle. Next, replicable. Next, closely approximate the ideal statistical properties of uniform and independence. Basics of pseudo-random numbers generators. Most Monte Carlo simulations do not use true randomness. It is not so easy to generate truly random numbers. Instead, pseudo-random numbers are usually used. The goal of this discussion is to provide a basic understanding of how pseudo-random numbers generators works, provide a few examples and study how one can empirically test such generators. The goal here is not to learn how to write your own random number generators. The typical structure of random number generator as follows. There is a finite set of S states. Finite set of S states and functional F. There is an output space and an output function G S U. We will always take the output space to be 0, 1. The generator is given an initial value S0 for the state called seed. The seed is typically provided by the user, then sequence of random numbers is generated by defining Sn is equal to F Sn minus 1 and 1 to up to un G Sn. There is nothing random here. If we generate a sequence of numbers with this procedure and then generate another sequence using the same seed, the two sequences will be identical since the state space is finite. Sn must eventually return to a state it was in simple or some time earlier. The smallest integer small p such as iterations is called the period of generator. Iteration is called the period of generator. Obviously, longer periods are better than short periods, but a long period by itself certainly does ensure a good random number generator. We list some of the properties we want in our generators. One by one, I am going to discuss the properties. First is the pass empirical statistical test. There are tests where you generate a long sequence of random numbers and then perform various statistical tests to test the hypothesis that the number of uniformly distributed on 0 to 1 and are independent. Next is the mathematical basis. There is a lot of mathematical theory behind these random number generators, including properties that should produce a good random number generator. Obviously, we want a large period, but there are more subtle issues. Next is the fast. And not a lot of memory. Most Monte Carlo simulations requires a large number of random numbers. We want to generate a large number of samples, and the generation of each sample often involves calling the random number generators many times, so the RNG needs to be fast. With most generators, memory is not really an issue, although some can take up a lot of cache. Next is the multiple streams. It is easy to use parallel computation for Monte Carlo, but this requires running multiple copies of your random number generators. So you need to be sure that these different streams are independent of each other. Next is the practical concern. Ease of installation and ease of seeding. Some random numbers generators are quite short and only take a few lines of code. Others are considerably more complicated. Some, like the Mercedes twister, require a rather larger seed. Many of the better generators use 64-bit integers, so be sure you are working on a 64-bit system and type your variable appropriately. Next is the reproducibility or reproducibility. For debugging and testing purpose, you want to be able to generate the same stream of random numbers repeatedly. For any random number generator of the form we are considering, this is easy. Just start with some seed. Next, linear congruential generators. Linear congruential generators. The state space is 0, 1, 2 up to m minus 1, where m is positive integer. Fx ax plus c mod m, where mod m means we do the arithmetic mod m. The constant a and c are integer and there is no loss of generality to take them from 0 up to m minus 1. For the output function, we can take gx as x by m. The quality of generator depends on the choice of the constant a and c. There is a lot of mathematics behind how these constants should be chosen, which we will not go into. Next is the multiple recursive generators. We take state space to be 0, 1, 2 up to m minus 1 and define the function f by xn, that is a1 xn minus 1 a2 xn minus 2 up to ak xn minus k mod m. The notation is inconsistent here because xn was the state at time n. Now the state at time n is xn minus 1 and xn minus k plus 1. Then the output is un is equal to xn upon n. With suitable choice of m and ai, we can get a period of m to the power k minus 1. There are more complicated linear generators. Example, matrix multiplication, recursive generators, generalized feedback shift registers, and twisted generalized feedback shift registers. But we do not discuss them. A widely used example of the latter in the measure twister MT19937, invented by Mastrukova and Mr. Moore, that's implemented in MATLAB and SSP. SPSS. It has a very large period, that is 2 to the power 19937 minus 1. Code for it can be found. Next is the combining generators. A random trick in designing random numbers generators is to combine several not especially good random number generators. An example of which manual generator which combines three linear convolutional generators, the state space is M1 minus 1 cross 0 1 2 M2 minus 1 cross 0 1 2 M3 minus 1. We denote the state at step n by xn, yn, zn. Then the generator is xn, that is 171 xn minus 1 mod m1, yn, that is 172 yn minus 1 mod m2, 170 zn minus 1 mod m3, where m1 30269, m2 30307, m3 30323. Output function un is equal to xn upon m1, yn upon m2, zn upon m3 mod 1. The period of approximately 7 to the power 12, large but not large enough for large scale Monte Carlo. We can also combine multiple recursive generators. L secures MRGs 32K3A is an example which employs two MRGs of order 3, such as xn is equal to 1403580 xn minus 2 8107 28 xn minus 3 mod m1, yn, that is 527612 yn minus 1 1370 589 yn minus 3 mod m2, with m1 2 to the power 32 minus 209, m2 2 to the power 32 minus 22853. The output functions, that is ut, that is xn minus yn plus m1 upon m1 plus 1, xn minus yn upon m1 plus 1. If xn yn xn yn, the period is approximately 3 into 10 to the power 57. Generator is implemented is MATLAB. A little statisticals or static analysis. Briefly explain two statistical tests: goodness to fit and the Kolmogorov-Simorov goodness to fit test. These are worth discussion not just because they are used in testing random number generators, but also because they are used to analyze what comes out our Monte Carlo simulation. So first, the square distribution. Let Z1, Z2 up to Zk be the independent random variables, each of which has a standard normal distribution. X is the k from a zi square. The distribution is called x square distribution. Obviously, it depends on the single integer parameter k. K is called degrees of freedom. Degrees of freedom. Next is the multinomial distribution. This is a discrete distribution. Fix a integer k. Probabilities small p1, small p2 up to pk, which sum to 1. Let x1, x2 and xn be independent random variables with values in 1, 2, k and p. xj is equal to 1, that is pi. Let oj be number of x1, x2 up to xn that equals j. O stands for observed. This is the observed number of times j occurs. There is an implicit formula for the joint distribution O1, O2 up to OK, but we will not need it. We will refer to the parameter n as the number of trials. Note that the mean of OJ is P, J, and suppose we have random variables O1, O2 up to OK, and we want to test the hypothesis that they have the multi-normal distribution. We let EJ, that is NPJ, the mean of OJ, and consider the statistical V from J is equal to 1 to K O J minus E J square upon E J. Theorem 1. If O1, O2 up to K has a multi-dimensional distribution, then as n tends to infinite, the distribution is of V defined above convergence to the x square distribution with k minus 1 degrees of freedom. Theorem 2. Let x be a random variable with a continuous distribution function f(x). Let u f(x), then the random variable u is uniformly distributed on 0 to 1. Tests for pseudo-random numbers generators. In the following, we let un be the sequence of random numbers from our generator. We want to test the null hypothesis that they are independent of each. Un is uniformly distributed on 0 to 1. In the following, the null hypothesis, we always mean the hypothesis that un are ID and uniform on 0 to 1. is first one is the equidistribution test. Equidistribution test. Another way to test that U and B uniformly distributed is to just use the Kolmogorov-Smirnov test. Hence, fx is equal to x. Note that this does not test independence of un at all. Another way to test the uniform distribution is following. Fix a positive integer m, let yn is un, where x is the floor function. We just round x down to the nearest integer. Next is the gap test. Fix a interval alpha, beta, 0, 1. Let Tn be the times when the random number is in alpha, beta. Let Zn be the gaps between these times. Zn is equal to Tn minus Tn minus 1. If the random numbers are IID and uniform, then Zn should be IID with a geometrical distribution with parameters P equal to beta minus alpha. We can test this with square test. Fix an integer r and take the classes to be z is equal to 1, z is equal to 0 up to z is equal to r minus 1, where r and z are connected by this. Next is the permutation test. Next is the permutation test. Use the RME to generate random d tuples of numbers u to the power 1, u to the power 2 up to u to the power 2. For each d tuples test, let pi be the permutation which puts them in increasing order. So far, pi 1, pi 2, pi 3, u, pi d. Under the null hypothesis that the random numbers are IID uniform, the permutations will have the uniform distribution on the set of d factorial permutations. We can test this with a x square test. Next is the rank of binary matrix test. Rank of binary matrix test. This one look pretty crazy, but it has been useful in showing some R and G's that pass some of the simplest tests are not good. Convert the IID sequence UN to IID sequence Bn with only takes on the values 0 and 1 with probability 1 by 2. For example, let Bn be 0 if Un less than 1 by 2. Bn is equal to 1 if Un greater than or equal to 1 by 2. Fix integer r and c such as r and c. Group the Bn into groups of size rc and use each group to form an R cross C matrix. Then compute the rank of this matrix using arithmetic mod 2. There is an implicit formula for the distribution of this rank under the null hypothesis. We can then do a x square test For example, take R is equal to C is equal to 32. The rank can be at most 32. Note that it is very unlikely to get a rank a lot less than 32, so you don't want to take classes running over all possible values of the rank. With R is equal to C is equal to 32, we could take a classes to be R30, R31 and R32, where R is the rank. Next is the two-stage or second order test. Consider one of the above tests. Let T be the test statistics. We assume that the distribution T under the null hypothesis is known. The simple test is to generate a sample, compute the value of T and then compute its p-value. A small p-value, example less than 5%, means we got a value of T. That is pretty unlike if the null hypothesis is true. So we reject the null hypothesis. Now suppose we repeat this 50 times. So we get 50 values of T1, T2 up to 50 of the test statistics. We then get 50 p-values even if the null hypothesis is true. We expect to get a few p-values less than 5%. So we should not reject the null hypothesis. If we do, but we use our 50 values of T to carry out a second order test. If the null hypothesis is true, then T1, T2 up to 350 should be a sample from the known distribution of the test statistics. We can test this with case statistics and compute a single p-value. We test if the Ti do follow the distribution. Thank you.